Welcome to the first lecture for Module 4 of the course Linear Algebra and Calculus. In this module, we are going to learn about sequences and series. A sequence in everyday language means a succession of things in a definite order. In mathematics, the term sequence is used to denote a succession of numbers whose order is determined by a rule or a function. Informally, a sequence or an infinite sequence is an unending succession of numbers. We call these numbers terms. It is understood that the terms are in order. There's a first term A1, second term A2, and so on. So we would write a sequence as A1, A2, A3, A4, etc. So here these dots are used to indicate that the sequence continues indefinitely. Some examples of sequences are 1, 2, 3, 4, etc., the sequence of all natural numbers, or a sequence like 1, 1 by 2, 1 by 3, 1 by 4, etc. For each of these sequences, we have a definite pattern that makes it easy to generate additional terms if we assume that those terms follow the same pattern as the first few terms. But these patterns can be deceiving, so it's better to have a rule or formula for generating the terms of a sequence. So to do this, we will look for a function that relates each term in the sequence to its term number. For example, look at the sequence 2, 4, 6, 8, etc. Each term in this sequence is twice its term number. That is, the nth term in the sequence is given by the formula 2n. So we denote this by writing the sequence as 2, 4, 6, 8, etc. 2n. The function f of n equal to 2n, we call this the general term of this sequence. Now, if we want a specific term in the sequence, we just need to substitute its term number in the above formula. So, for example, the 37th sequence in the term in the above sequence is 2 times 37, that's 74. One important idea which we'll need is the limit of a sequence. A sequence has a limit L or converges to L if limit n tends to infinity an equal to L. Or, in other words, an tends to L as n tends to infinity. If such a number does not exist, the sequence has no limit or the sequence diverges. Let's look at an example. Does the sequence e raised to 3n divided by 4n converge? If we rewrite the sequence as a function of x, we get f of x equal to e raised to 3x divided by 4x. This is the general term of the sequence. Now take the limit x tends to infinity. To find the limit of this term, we will apply L'Hopital's rule. Then limit x tends to infinity e raised to 3x divided by 4x is limit x tends to infinity 3 e raised to 3x divided by 4. This tends to infinity. This f of x, the general term, is divergent. Hence, the given sequence is also divergent. Next, we will look at infinite series. An infinite series is an expression that can be written in the form sigma k equal to 1 to infinity uk equal to u1 plus u2 plus u3 plus etc. plus uk plus and so on. The numbers u1, u2, u3 in this case are called the terms of the series. Now, if we have a series sigma n equal to 1 to infinity an, define the sequence Sn, where Sn is the sum of the first n terms of the series. Given a series sigma n equal to capital N to infinity an, define the sequence Sn, where Sn is the sum of the first n terms of the sequence. This sequence is called the sequence of partial sums. So S1 is just the first term, S2 is the sum of the first two terms, S3 is A1 plus A2 plus A3, and so on. So for example, if an is 1 by n plus 2, then S1 is A1, that's 1 by 1 plus 2, 1 by 3. S2 is A1 plus A2, that's 1 by 1 plus 2 plus 1 by 2 plus 2, this is 7 by 12. This way we can evaluate the sequence of partial sums. Given a series sigma an, and if its sequence of partial sums is Sn, then if limit n tends to infinity Sn is equal to S, we say that the series converges or the series is convergent. If the limit of the sequence of partial sums does not exist, then we say that the corresponding series is divergent or diverges. If Sn has a limit capital S, S is called the sum of the series sigma an, and we will write sigma n equal to n to infinity an equal to S. So in other words, the series sigma an converges if and only if the sequence of partial sums Sn converges. Next we have the divergence test for checking whether a series converges or not. This test says, if limit n tends to infinity an is not equal to 0, then the corresponding series sigma n equal to 1 to infinity an diverges. For example, take the series sigma n equal to 1 to infinity n divided by square root of n square plus 1. The general term an of this series is n by square root of n square plus 1. Take the limit of this general term. So limit n tends to infinity, n by square root of n square plus 1 is equal to 1. The divergence test says, if this limit is not equal to 0, then the series diverges. So we can conclude that sigma n equal to 1 to infinity, n by square root of n plus 1 is a divergent series. Next, we will look at some special series. The first one is geometric series. This is quite similar to geometric progression. So the series sigma n equal to 1 to infinity a r raised to n minus 1, where a and r are constants and a is non-zero, is called a geometric series. The geometric series sigma n equal to 1 to infinity a r raised to n minus 1 converges and has a sum a by 1 minus r if modulus of r is less than 1. The geometric series diverges if modulus of r is greater than or equal to 1. For example, determine whether the series sigma n equal to 1 to infinity 3 by 10 raised to n converges or diverges. If it converges, find its sum. The series is sigma n equal to 1 to infinity 3 by 10 raised to n. If we rewrite the term a little bit, we will get sigma n equal to 1 to infinity 3 by 10 times 1 by 10 raised to n minus 1. This is a geometric series with a equal to 3 by 10 and the common ratio r equal to 1 by 10. Since the modulus of r is 1 by 10, that's less than 1, so this geometric series converges. As this is a convergent series, we can find its sum a by 1 minus r, that's 3 by 10 divided by 1 minus 1 by 10. This is equal to 1 by 3. Next example, express 0.737373 etc. as a ratio of integers. So we can write this repeating decimal as 0.73 plus 0.0073 plus 0.000073 and so on. By comparison, this is a geometric series with common ratio r equal to 1 by 100 or 0.01. And the initial term of the series a is 0.73. So the sum of this series is a by 1 minus r, 0.73 by 1 minus 0.01. This gives us the rational number represented by this repeating decimal. It's 73 divided by 99. The next example of a special series is the p-series. The p-series is defined as sigma n equal to 1 to infinity 1 by n raised to p, where p is some constant number. As for the geometric series, we have a condition to check whether a given p-series converges or not. So the p-series sigma n equal to 1 to infinity 1 by n raised to p converges if p greater than 1 and diverges if p is less than or equal to 1. So when we let p equal to 1, this is sigma n equal to 1 to infinity 1 by n raised to 1. This is 1 plus 1 by 2 plus 1 by 3 plus etc., which is the harmonic series, and it diverges. On the other hand, let's say we had the series 1 plus 1 divided by cube root of 2 plus 1 divided by cube root of 3 plus etc. This is a p-series with p equal to 1 by 3. This series also diverges.